Okay, thank you very much. My name is Lennart Beringer, and I'll be reporting on work that I did jointly with Katherine, who's an undergraduate at Princeton, advised by Andrew Appel, and also Adam Petcher, who finished his PhD this spring at Harvard and was also associated with MIT Lincoln's lab. And the issue we're studying here is to investigate in how far formal methods, in particular interactive theorem provers, can help us as a defense mechanism against attacks, in particular on cryptographic primitives as implemented in libraries such as OpenSSL. And I'm sure this does not need a lot of introduction and motivation here. Let's just remind ourselves about one of the most recent attacks on everyday items, the attack on vehicles by Charlie Miller and Chris Walasek, extending earlier work by Stefan Savage, who was in the audience this morning. And they demonstrated that it's possible to take over vehicles while they're running remotely, and manipulate brakes and acceleration and all these kinds of things. And of course, this is hardly the only everyday item that makes the news these days. So just over the last week, I think various other items were reportedly compromised. And while all the details differ in these attacks, there are some general patterns that reappear, and one are the exploitation of memory vulnerabilities, and a second item is that both the systems as a whole, but also individual components on the systems are insufficiently isolated from each other, in particular by cryptographic mechanisms. So one particular lesson is that maybe components, for example, on a bus, shouldn't really accept arbitrary messages from other components unless they are properly authenticated. Now, this is, of course, well known and to everybody, but still maybe not followed always. And one way to do such authentication is symmetric-key authentication, which is essentially a kind of checksum computation. So imagine a sender and receiver of a message. They have previously agreed on a key that they share. They both combine this key with a message in a predefined manner, applying this MAC algorithm shown there in red to calculate this checksum. The sender transmits his checksum together with a message, and the receiver validates that the received checksum is identical to the one he computed, and only then does he accept the message as being authenticated. So the particular scheme that we looked at is the so-called hash-based message authentication, HMAC, which was introduced about 20 years ago in this paper mentioned there at the bottom. And there, this calculation of the checksum involves the application of a cryptographic hash function. In our case, later we'll specialize that to SHA-256. So if we want to understand what this HMAC actually does, well, the generic point to start from is the FIPS document shown here, and with a little bit grain of salt, this is roughly what happens. So income at the top, data and a key as a list of bytes. The key is then normalized and, if necessary, padded, and is then combined with a key and sent through the hash function SHA-256 twice, in each case manipulated or combined XORed with two particular constants that are given in the standard. And the result of the outer application of that is then the overall checksum. So, of course, a standard is not directly in implementation, so we should ask ourselves what could go in principle wrong, or what issues you need to take into consideration when you want to use and implement such a scheme. Well, first of all, the people who introduced the HMAC are eminent cryptographers, so probably they didn't make a mistake, but on the other hand, the paper is just written in LaTeX, and during typesetting, mistakes may have emerged that nobody missed, but at least we have something to start from. They proved that HMAC is a pseudo-random function under the assumption that the underlying hash function is a pseudo-random function, plus a couple of additional assumptions, but they state them all.
Historically, actually, the first two versions of HMAC had flaws. We were really dealing with HMAC 3.
Right.
So even cryptographers make mistakes.
Okay, good. Just to my point. Right. So once that has possibly eliminated, the standard is not exactly the same as the original paper. It is formulated using byte sequence, whereas the original paper is formulated over bit lists and things like that. So you may wonder whether some mistake snuck in there. Next, when you have actually an implementation, you will, of course, want to know whether it computes the function correctly, or whether the implementers misunderstood the standard in some way. Next, C programs are notorious for having sometimes or additional memory access operations that you may at least find surprising, buffer overruns and all these fun instructions that we're all aware of. Next, it's not entirely obvious whether the implementer of the C program and the compiler writer actually had the same interpretation of the C standard. Particularly as compilers get more aggressive regarding their optimization, they exploit more corner cases of the C standard, and the implementer may not have been aware of all of those. Of course, the compiler may itself have bugs. That is certainly not news, and it's in particular important to know what kind of correctness statement the compiler actually should or does satisfy. And underlying of all of that, of course, is a processor, and it would at least be good to know on what kind of basis the compiler may or may not be correct, let alone low-level attacks such as timing or cache-based attacks. So clearly, there's some framework and approach needed so that we can gain additional confidence on implementations, and that's what we set out in this project. What we provide is a machine-checked proof of functional correctness and also of cryptographic correctness of a particular implementation of HMAC that we derived from OpenSSL. And the same holds for the underlying implementation of SHA, and all this in the interactive proof assistant COC. You can see there the components of our system. Underlying at the bottom is a verified C compiler CompCert developed by w.r.t about 7 years ago or so, and that indeed rests on a particular specification and description both of the C language and of processor instruction set architectures. On top of that, there's the Verified Software Toolchain, which is a program logic developed by Appel's group in Princeton to reason about C programs. We can use that, in particular the proof automation for that, to verify concrete programs, the C programs there, with respect to descriptions in COC of the HMAC and SHA functional specifications. Now at the very top, the three boxes there concern the cryptographic proof, and for that we use a tool developed by my co-author Adam Petcher. FCF stands for Foundational Cryptography Framework, and that allows you to reason about cryptographic primitives and probabilistic reasoning inside COC. And so finally, we then had to combine the two systems. So overall, we get the correctness of the C code with respect to the function specification, the cryptographic verification at the top, and all that is linked. And because of some particular forms that the logic takes, we also get memory safety and those kind of non-leakage and integrity properties that come from guarantees that a program will not access memory areas outside the specification. to give you some details, this is sort of one of the starting points for the C verification, and this is essentially the transcription of the picture I showed you earlier into the programming language inside COC. So you see there, roughly in the middle, the definition of the HMAC 256 function, which takes a message and a key, normalizes the key, and then applies the HMAC core function, which has this double-nested application of the hash function 256. And here, in contrast, so everything is formal here, contrast to the informal standard. So we can use that fact to later on reason mathematically inside the proof assistant about that implementation. And also, it is an executable specification. You can run this program both inside the theorem prover or extract it to OCaml and run test cases. Now, if we look at an implementation, then it's not immediately obvious how it relates to the functional specification. So this is the API of OpenSSL. So in particular, it uses a so-called incremental understanding, which allows you both to provide a key and use it for several messages. So you can think of it as a session key, and also to provide the data itself in chunks before finally wrapping everything and computing the overall HMAC code. The protocol is there shown as a simple state machine. All that is visible in the header file of C, and so is a struct, the data structure there that contains 3 internal SHA data structures and also 2 additional fields. I should say that these 2 fields there shown at the end, we actually identified during our verification to be not strictly necessary, and Adam Langley's effort on Beringer SSL made essentially the same observation roughly at the same time, so on the following slides I won't be even showing those 2 fields. I should also say that this is a slightly outdated interface of API. It's a statically linked version. Modern versions of OpenSSL and also Beringer SSL use envelopes, which are sort of homebrew object system with function pointers. So our logic does support reasoning about those, but we didn't exercise this on this particular code. So in order to link this implementation to the COC code, to the functional specification, it proceeds in several stages. First of all, we have to model the structure of this API in the proof assistant. So there in the inductive definition that defines the correspondence of the pink struct as a value in COC consisting of 3 abstract representations of the SHA constituent states. Once we've done such a definition, we can then write in COC specifications for the components of the incremental API, the predicates init, update, and final there, just as properties about relating various such abstract states. And these definitions, of course, refer to similar definitions for the SHA functions. We can then verify that the expected sequence of initializing, updating, and finalizing such structures results in a correctly computed value. So that's the first step. And the second step is that we do something similar, but now not for COC values, but really for the C values as laid out in memory by a C program. So that results there at the bottom of the blue box in a assertion in this separation logic that specifies that at pointer or address C there is a layout of this particular struct HMAC context called R, and that relates actually to the abstract states that we defined on the previous slide as specified by these auxiliary definitions. Now, once we've done that, we can actually write a specification of our functions. Here, this is the one for the HMAC update function. It has, as is typical for HOR verification systems, preconditions and postconditions. They come here in a slightly stylized form, and in particular, these clauses there marked with SEP are clauses that talk about the heap. So. And in particular, the items in these lists are by definition interpreted to talk about disjoint regions of the memory. So essentially that specification there says sort of if D holds a data that you want to update the HMAC with, and your representation currently is at C, then after applying the update function, you've updated H to H1 and the data is unchanged. Now, we do something similar for the overall HMAC function. And the details here are not so important, but again, we have ensured in the specification that both the key and the message are preserved, and in yellow there we have the condition about the final result. And also as a guarantee of this logic, this ensures that no other memory areas outside the ones specified there will be accessed during execution. Now, once we've specified all these functions, of course, the fun only starts. Now we have to verify it. And that is done interactively using a forward symbolic execution over these VST proof rules. So you see here a snapshot of Coq's interactive development environment, where you have on the left a proof script that you write interactively and can process step by step. And on the right-hand side, you see the corresponding proof state that results from executing such a script step by step. And particular below the line there is the goal that you're currently proving with a precondition and the code representation there at the bottom. And the proof then proceeds by stepping through the script on the left. Here we're about to execute the proof tactic for a function call that does a lot of automation in the background and will then update the proof state on the right. And hopefully we will successfully complete that all the way down to the QED, at which point Coq will check the proof and make sure everything is correct. And all of this is directly carried out inside Coq, operating on the same abstract syntax tree that CompCert actually sees when compiling the program. Now let me briefly say a little bit about the cryptographic part of our proof. Well, that, as you'd expect, starts from the original paper by Beringer and his collaborators. And if you look at that again, it's not immediately obviously the same as the FIPS standard. So it mentions explicitly that the hash function is one of the follows the iterative construction of Merkle-Damgard. It mentions some slightly different construction, NMAC, that is actually a stepping stone to defining HMAC then. And hooray, it also claims and proves a property about the function computed. To verify that, we use, as I mentioned before, Adam Petcher's Foundational Cryptography Framework, and that is essentially a probabilistic programming language embedded inside Coq as a shallow embedding with means for sampling uniform random bit vectors and library of probabilistic distributions and lemmas for reasoning about such distributions and for bounding differences between them and to prove them equivalent. And in particular, this library can be used to formalize a kind of proofs occurring in the cryptographic literature called game-based proofs, where you take the picture of an adversary interacting with oracles that can maintain internal state. And in this case, the state could be that inside the oracle is a function that is either a true pseudo-random function or this HMAC function. And the adversary, after interacting with the oracle, emits a bit and essentially has to tell these two situations apart. And the idea is that we can bound the success probability of such an adversary for the HMAC versus pseudo-random function oracle by the assumed hardness of the hash function, which can also be modeled as such a game. So again, an adversary interacting with a slightly different oracle. And the result is there shown at the bottom. So we can bound the advantage of the adversary A for HMAC from above by the advantage of a certain different adversary B against the hash function, plus two other terms that model the advantage of yet further adversaries against oracles that model the other two assumptions of the proof that I'm omitting here. Now here, this function HMAC shown there in red is of course a formalization of Belaire's definition, so it's in particular bit-oriented, refers to NMAC, and is iterative according to Merkle-Lamgard, and that just facilitates an easier comparison of what is modeled here with the original result, and also allows us to follow the proof described in the literature more easily. But of course it means that we have to bridge the gap between the two programs inside COC now. Now luckily, since everything is now a functional program inside COC, these proofs can be done independently of any C implementation issues or cryptographic facts. And here we show the 6 differences that the two programs actually have, and we prove equivalence of these programs essentially by defining 5 intermediate definitions of HMAC, and in each stage proving the functional equivalence of the computations. Now, to conclude, we've arrived at a formal verified stack of arguments that together ensure both the implementation and the cryptographic correctness of HMAC, all end-to-end in a single environment given by the COC proof assistant. Now, clearly, this is not the solution of all security problems, and in particular, more automation clearly will be needed to scale this up to significantly larger systems. On the other hand, these are real pieces of software that can nowadays be done. So proof automation and interactive theorem provers have indeed come a long way over the last years. In the future, we'd like to indeed link this to additional items of a system stack, such as protocols. There are by now also operating systems that have been formally verified. That would be certainly interesting to combine, and also extend the attack models by considering possibly timing or other channels by using more refined processor models, and maybe even considering issues such as security-aware correct compilation. And overall, that still will not allow us to verify all the software out there, but maybe for certain pieces of critical systems, it may become more viable than it has been in the past, and whether that will include the car hacking domain, I'm not sure yet. Thank you very much.
Shuchen, Microsoft Research. Very interesting work. So my question is, who provided the functional specification of HMAC? It's you or some prior work?
Yes. No, we derived that from by reading the FIPS standard like everybody else does.
Do you try to prove whether this set of functional specifications achieve some end-to-end goals?
Yes.
Is there a definition about end-to-end security of HMAC?
Yes, it is this functional program that I showed there. We show in the upper part of that proof that it is a pseudo-random function, in this precise way specified in this theorem I showed on the previous slide.
I see. Yeah, thank you.
You're welcome.
Hello, Hannes Minert from University of Cambridge. And I have one question. So I've been working on InCog and formal methods, and I would like to know how many person years did you spend on the formal verification of the HMAC 256 in total?
Well, sort of the tools both at the bottom of the stack, CompCert and VST, are sort of infrastructure projects that have been developed over several years, including proof automation and all this. For HMAC itself, I think the first verification of the C code plus the modeling in COC was a matter of, I don't know, 6 weeks. And I wasn't particularly familiar with the optimization and the proof automation tactics because of the VST, because I worked more on the CompCert part for the previous project. And roughly for the HMAC at the top there, the cryptographic part, I think that was also more a matter of weeks than of years. Certainly.
Hi, Patrick Hewlin, MIT Lincoln Lab. I was going to ask the previous question, but I have a sort of a follow-up. How do you think that so I've played around with this stuff maybe 3 or 4 years ago, but how do you think the sort of proof automation technology has been progressing? Because that always seemed to be, to me, maybe 3 or 4 years ago, to be the
Sure.
biggest problem with doing this on any scale.
Yeah. Yeah, so regarding the cryptographic part, I believe that FCF is a little bit similar to earlier tools that you may have seen coming from the IMDEA Institute in Madrid, developed by Gilbert's group, follow roughly similar goals. I believe it is a little bit less expressive, but slightly more convenient to use. Adam Petcher would probably be a better person to discuss the details. And regarding the program logics, so 5 years ago, the VST didn't fully exist yet, so certainly the automation for that has improved, and it's really different between different systems as implemented in theorem provers. So there are new techniques coming up, and COC is getting more powerful, and the improvements in underlying hardware help us, but yes, it's still sometimes a little painful.
Okay, thank you.